আসসালামু আলাইকুম সবাইকে। আশা করি সবাই ভালো আছেন এবং সুস্থ আছেন। আপনাদেরকে বাংলাদেশ অ্যাস্ট্রোনমি রিসার্চ সেন্টারের এই স্পেশাল লাইভে টকে স্বাগতম। আজকে আমাদের সাথে আছেন ভেরি স্পেশাল একজন গেস্ট, যিনি কথা বলবেন আমাদের স্টেলার ইভলিউশন বা নাক্ষত্রিক বিবর্তনের উপর। প্রথমেই আই উড লাইক টু ইন্ট্রোডিউস আওয়ার গেস্ট মাইশা ইয়াজিদি ম্যাম, যিনি হচ্ছেন তিউনিসিয়ান অ্যাসোসিয়েশন অফ ইয়াং অ্যাস্ট্রোনমার্স এর প্রতিষ্ঠাতা এবং তার সাথে তিনি কাজ করছেন ইন্টারন্যাশনাল অ্যাস্ট্রোনমিক্যাল ইউনিয়ন বা আইএইউ এর তিউনিসিয়ার ন্যাশনাল আউটরিচ কোঅর্ডিনেটর হিসেবে। তিনি কাজ করেন এবং গবেষণা করেন জ্যোতির্বিজ্ঞান নিয়ে। আর আমি আছি হাসিবুল হোসেন রিফাত, বার্কের পক্ষ থেকে। এছাড়া আমিও কাজ করছি ইন্টারন্যাশনাল অ্যাস্ট্রোনমিক্যাল ইউনিয়ন বা আইএইউর সাথে বাংলাদেশের ন্যাশনাল ইভেন্ট কোঅর্ডিনেটর এবং ভলান্টিয়ার হিসেবে। আমাদের বাংলাদেশের ন্যাশনাল আউটরিচ কোঅর্ডিনেটর হচ্ছেন আমাদের শ্রদ্ধেয় আমার প্রিয় ফারসিন মান্নান মোহাম্মদী স্যার। আমরা এখন দুই দেশ থেকে লাইভে এসেছি। আমি বাংলাদেশ থেকে এবং ম্যাম এসছেন ইটালি থেকে। যেহেতু ম্যাম ইটালিতে পিএইচডিরত অবস্থায় আছেন, তাই তিনি সেখানে অবস্থান করছেন। And in this event, a lot of people have registered. So I would like to say, please do comment below. Where are you from? আর বাংলাদেশ থেকে যারা দেখছো তারা অবশ্যই জানাও তোমরা কে কোথা থেকে দেখছো। আর যারা লাইভে জয়েন করেছো তারা লাইভ ক্লাসটি শেয়ার করে দাও সব জায়গায়, যেন সবাই লাইভ ক্লাসটি আমাদের অংশগ্রহণ করতে পারে। And those who are watching from outside Bangladesh, please share the live class. So without any further ado, let's get started. I will hand over the live class to my ma'am, Yazidi ma'am. So let's start.
Thanks, Hasibul, Hossain, Rifat, for the nice presentation. And also, I would like to thank him for the idea of this talk today. Also, I would like to warmly thank the working group of Bangladesh Astronomy Research Center for their amazing work to organize this event for today. So, warm welcome to all the participants with us nowadays, wherever they are here in the platform or following us in our social media. So today what we're gonna do, we're gonna talk about stellar evolution through the born, the life, and the end of stars. So I'm gonna start share my screen, and you should see it. So, okay, can you see my slide? Can you see my slide?
Yes, ma'am, we can see your slides.
Okay. So today we're gonna talk about the stellar evolution from birth to death and the solar cycle. So the first thing that I'm going to start is that I think what connects us nowadays, and this meeting is astronomy, is the curiosity to learn more about the universe, discover new things, and understand from where things are coming. Each one of us during his childhood and even still nowadays looking up to the sky, to the deep sky, to the planet, to the Milky Way, and to that Milky Way that contains several hundred of billion of bright stars of various size, age, and masses. Looking up to those stars at night and asking always the question from how it's come and how they form, how it become just like that. So stars are the most, in fact, widely recognized astronomical object and represent the most fundamental thing to understand the origin of the solar system, and by coincidence, the origin of our planet, the Earth. The distribution and the composition of the stars in the galaxy trace the history, the dynamic, and also the evolution of that galaxy. Moreover, stars are responsible for the manufacture and the distribution of heavy elements, like, for example, carbon, nitrogen, oxygen, and the characteristic of stars tie or directly connected to the characteristic of the solar system and also to the planets. Here is some picture of the European South Observatory of some beautiful image for the Milky Way. So the question here is how stars appear, how they come from, and how it started. The most important question. So in fact, it started in the 19th century by Immanuel Kant and also Laplace. Immanuel Kant is in fact a German philosopher, and Laplace, which is Pierre-Simon Marquis de Laplace, a French mathematician, and also he worked in statistics, physics, and astronomy. The idea of nebular cloud, or the nebular solar nebulae theory, started in fact by independent observation for Kant and Laplace, which the both of them here, they proposed a model for formation of the planet from a condensed material in the bottom of a protoplanetary disk called the protoplanetary disk, which is a cloud of material and molecular clouds rotating around a very young star that's gonna be in the future our sun. So the nebular theory, or the solar nebular theory, in fact is based to what? This theory based in the fact that stars are born in a molecular cloud, as you can see here. And I don't know if you can see my row. Here is stars are born usually in protoplanetary cloud, or in molecular cloud with low density. We call like molecular cloud. So the stars usually are born here out of the gravitational collapse of cool, dense molecular cloud or interstellar material. This cloud, in fact, is perturbed by a shock wave come from a nearby explosion of star or the arms of spiral galaxy. And here why we say spiral galaxy in particular, because usually spiral galaxy, they have like open arms and they can easily perturbate any closer object. Or another possibility is from other massive celestial object. So this cloud, in fact, is formed by 99% of hydrogen, but also some other heavy element and material with very low density. So the perturbation of this cloud by a possible solar explosion or possible spiral galaxy arms or another massive object that we don't know, generate the perturbation and consequently the compression of the cloud. This cloud collapse, and which generate afterward the gravitational collapse of these clouds. What's happened after that is that the most of particles go to the center of the cloud, which make the density much more higher, and as well the temperature, because if we are increasing the dimension, we are making the temperature much more higher and the density as well. But this stage happen, we are here in the second stage, this happen when we do have a very important condition, which is it should be the cinetic or the internal energy less than the potential energy. The cinetic energy is proportional to the mass of the cloud and the temperature, and also inversely proportional to the mass of the hydrogen atom. While the potential energy, in fact, is proportional to the mass of the cloud and inversely proportional to the radius of the cloud. So to have or to get the collapse of this primary cloud, we should absolutely have the cinetic energy less than the potential one. The cinetic energy also we can call the internal energy of the clouds. So following this equation, which give us a certain important condition, which is the instability of a gene. What is the instability of a gene? Here we're going to talk about the gene mass and also the gene radius of the cloud. The instability of gene, in fact, is a certain parameter or a certain limit in which below this limit we cannot talk about star. We can talk only about a planet or brown dwarf. So the radius of a gene here is proportional to the temperature and inversely proportional to the mass of hydrogen atom and also the density of the cloud. The gene mass is proportional to the temperature and also inversely proportional to the density of the cloud. Here I expressed N as the density, and the mass of a gene is always expressed in solar mass. So if we consider that the mass of molecular cloud is greater, here's our condition. If we consider that the mass of cloud is greater than the mass of a gene, what's gonna happen is very important. Is that the particle in the center, if you're gonna back here, if we consider that the mass of the cloud is more important than the mass of a gene, what's gonna happen? This particle go to the center of the cloud, agglomerate by the force of attraction to burn the protostar, to let's say make particle much more and more bigger, and consequently what generate is we do have a protostar. But that happen, as I say, we should consider into this step two important condition, which is the energy, kinetic energy should be less than potential one, and we should talk about limit, which is limit for the radius and gene higher than the instability of a gene. Otherwise, you cannot have a protostar. So the magic step here is that when the protostar burn, here we do the gravitational contraction generate an important energy. And when we talk about energy, we talk about temperature. So when the temperature of the hottest star, of the protostar, because the energy gonna make the protostar warm, and consequently we're gonna increase the temperature of the protostar. So when this temperature achieve 10⁻⁷ degree Kelvin, yep, here we're gonna talk about a very important evolution of the protostar, which is the fusion of hydrogen into helium, which is the first chemical reaction. So then, a cloud of dust and gas. We are here in this step. We do have a protostar. We're gonna start. If you can follow my row here in the slides, here is the protostar, and we already started the nuclear fission of hydrogen and helium. Then a cloud of dust and gas result from the collapse, which is much more better here. Here's the protostar, and here we have a cloud of gas and particle result from the formation and the condensation of the particle to form the protostar, agglomerate together and condensate together to form a protoplanetary disk, which we can see here. Here is a star, and around the star we do have the protoplanetary disk, which is the embryos of the planet, with a size here closer to the size of Mercury, because these embryos, they are really small, they cannot form a real planet, but they are the embryos of the real planet. So then, all this procedure, in fact, depend in two important parameters, which are the phenomena itself, the evolution and the generation or the born of the star. It depends is two basic also things, which are Newton's law of universal gravitation, because particles are agglomerating together by the force of attraction, and the other important parameter is the angular momentum. So what the Newton's law of universal gravitation say? What this law say that if we have two bodies with successive masses m1 and m2, the two bodies, if they do have mass, consequently they attract each other with the force proportional to their mass and inversely proportional to the distance that separate their center. These force, in fact, help a lot to let the protostars and also the embryos of the planet form, because they agglomerate together and also they condense together to form a more and more higher project and important project. So then the next important parameter is the angular momentum. What is the angular momentum? The angular momentum, in fact, is a very important parameter in physics and astronomy, but also at the same time is one of the problems of the theory of nebular cloud, or the solar nebula theory. because it's also one of the issues that really does not go parallel to this theory. So the angular momentum depends mainly to the mass, to the radius, and also to the velocity of the project. In the absence of anything that cannot change or cannot modify the angular momentum, this angular momentum, in fact, remains constant. If there are no other extra force or external force can change it, so it's gonna still constant forever. Not forever, but for a long time. To explain it better, the good example is this figure, is a figure of a scatter spins. Here, if we're gonna consider that this scatter spin with open hands, her hands is so far from her body or her chest. So here we do have a very long radius. The radius here is very long from the left hand to the right hand. Here, this girl, she gonna turn or she gonna spin slowly with a slowly velocity. So what is consequently generate a slow or a small angular momentum, because as we say before, the angular momentum depends on the mass, to the radius, and to the velocity. So higher radius or large radius, which is the right and the left hand, generate slow velocity. That means if we increase the radius, we're gonna have a slow velocity and consequently a slow or small angular momentum. But if this girl, she gonna close her hand and make them closer to her body or closer to her chest. So what she did is she increased the radius, but she gonna turn so fast. Why? Because the radius and the velocity are the opposite. If we're gonna increase the radius, the velocity gonna go slow. If we're gonna increase the velocity, the radius gonna be more small. So here's the angular momentum. And this is the same example for a molecular cloud. In the beginning of the nuclear theory, the cloud was very large with very large radius. Here the radius of the cloud is very higher, but the particle in the clouds turn very slowly. When this cloud collapses and all the particles go to in the bottom of this cloud or in the center of this cloud, what we did in fact is just we are decreasing the radius of the cloud, and consequently what's gonna happen, we're gonna increase the radius of the cloud, we're gonna have a higher velocity for the particle. So particle here gonna turn so fast. So the angular momentum, which is the product of what? The angular momentum is the product of the angular velocity, which we expressed here by I, and the moment of inertia, which we expressed here by W. So the angular momentum gonna be constant. Why? Because if we're gonna increase the angular velocity, we're gonna decrease the moment of inertia. And if we decrease the moment of inertia, we're gonna increase the angular velocity. And consequently, the angular momentum gonna be constant. It's like equilibrium. If one increase, the other one decrease. If the other one decrease, the other one increase. And that's consequently generate a constant angular momentum in case we do not have any other force that can modify that, like twisting force, another force. So then, now we was talking about the protostar. Now, once the protostar is formed, let's consider that we do have a protostar, because the brown dwarf, the brown dwarf is a stage, as I say, if we have really a small size of the protostar, we cannot talk about star because we're gonna respect the genus and stability. It's a limit for certain mass, for certain radius that's below this limit. We cannot talk about star. We can talk only about dwarf or a brown dwarf or a planet. So for a mass less than 0.08 solar mass, we cannot talk about star. We cannot talk about brown dwarf. So, as I say, why we don't have a star here? The question is, to answer this question, in fact, because the temperature is not really higher enough to start the fission of hydrogen into helium. And the radius of the protostar here, which is a slow radius, is closer to a gasific planet because the mass is not really enough, the radius is really small, and the temperature is not enough to start the fission of hydrogen into helium. So here we cannot talk about star, we can talk only about dwarf, brown dwarf. The next case is, what about if the mass of the protostar is something between 0.08 solar mass and 8 solar mass? Here, the possibility is in fact, the result is very clear because we're gonna have a sun, a solar like our sun. So here the temperature in a mass between 0.08 and 8 solar mass, we're gonna have enough temperature that could generate the fission of hydrogen into helium. So in that case, we're gonna have sun, like our sun, that afterward gonna become red giant, and afterward we're gonna give us white dwarf and our supernova A1. We're gonna see it in the next slides. But the question, what about if the protostar have really a very important mass, like a supergiant protostar? What we're gonna have? The answer is very easy, because if you have a very important mass for the protostar, we're gonna have a blue giant, a very big star, in which we're gonna generate in the future black hole or a neutron star, which is much more complicated things. So, to summarize, this slide in fact summarizes the different steps that the sun or the protostar can pass through. Here in the top left, we can see the evolution of the protostar according to their masses. For a small protostar, we can have a brown dwarf, and they end their life as a brown dwarf. For the protostar, we're gonna have much more bigger, we're gonna have the same brown dwarf and become red dwarf, and gonna end her life white dwarf because of the next step after the red dwarf. If we have protostar with a respectable good mass, what we're gonna have the sun, like our sun, but that after that gonna generate the red giant, and afterward what is gonna generate the planetary nebula. How it's gonna generate the planetary nebula? This step is important because it's gonna let us understand what's gonna be the future of our sun. In this step, the sun generate only carbon, from hydrogen to helium, from helium to carbon, and then she's gonna stop at that level of nuclear fission, because they do not, in that level, the star don't have enough temperature to go to the next step, which is to burn the carbon to generate the neon. So in that step, the outer layer of the star here, the outer layer, we stop it here at the carbon level because we cannot generate the neon. So the outer layer of the star here expand, resulting in period of mass loss. They're gonna lose the mass here in the outer layer of the sun. They're gonna lose mass, and they're gonna just extend in the universe. Eventually, the outer layer of the star are ejected completely and ionized by the white dwarf to form a planetary nebula. So here, after we have the planetary nebula, we're gonna have white dwarf, or if it's merged with another brown dwarf or another celestial object, we're gonna have a type A1 of supernova. So if the mass is much more bigger, we're gonna have a blue giant and then red giant, and from the red giant, if it's merged with another blue giant from other part of the universe, we're gonna have type 2 of supernova that's gonna generate the neutron star. And also for the rest of the protostar's masses, here we can have, according to the protostar masses, we're gonna increase the complexity or increase the importance of celestial object. We're gonna have type 2 supernova for much more higher mass of a protostar, and then gonna have black hole. So then the important step is, here I'm gonna show you first some real image from NASA's Spitzer Space Telescope, which is show here a very beautiful and cool image of the protoplanetary disk. Here's a picture taken by Spitz in 204, and here is in 208. It shows here in 204 we have, like, if you can follow my row, we can see here that we do have something is like, it's not really a protostar, or it's not really a protoplanetary disk, but we can see like there's something here is trying to form. After just 4 years, we succeeded to see that we do have here protostar and we do have protoplanetary disk. This is a real image from Orion Nebula, which was taken by Space Telescope. And here also another cool image from Hubble Space Telescope show different protoplanetary disk here. This protoplanetary disk located around like 1,400 light year from us. And here also another protoplanetary disk taken also by Hubble Space Telescope. But this one are located in 1,400 light year from us, and they are located in Mayssa 41. And here also another protoplanetary disk, and this image was taken by the ESO, or European South Observatory, of the protoplanetary disk. Then we're gonna pass to a very important diagram, which is called HR diagram, or Hertzsprung-Russell diagram. An important tool in the study of the stars' evolution. Why? Because this diagram, in fact, very important to understand the evolution stage of the stars. So this kind of diagram developed in the 19th century by Ejnar Hertzsprung, which is a Danish chemist and astronomer, and also Henry Norris, which he is American astronomer. This diagram, in fact, plots the absolute magnitude of stars against their spectral type, or alternatively, the luminosity versus the temperature. So here I'm going to show you a very cool thing, which is, here's the first HR diagram, which was carried out in 1914, and it was published in the Nature. And here is a Nature journal, and here is the first paper of Ejnar, in which he was talking for the first time about red giant and red dwarf stars, and it was published in 1905. So stars, in fact, began their lives in the main sequence stage through the ignition of hydrogen and occur. We can see here's the main sequence. Usually stars start their life in this sequence, and then from this sequence they evolve, or they migrate to another part of the diagram. From after, the life of the stars is simply described as the evolution of gases mass through well-defined stage of equilibrium between the gravitational energy and the energy produced by the nuclear reaction into the core, because the evolution of stars, in fact, is linked or is tied or directly connected to the mass. So stars, in fact, evolve. So it's moved to specific region, whatever they are, the white dwarf, the supergiant one, or the giant one. So the HR in the HR diagram here. So following the characteristic path that depends in the star's mass and chemical composition, because here, if we're gonna consider the white dwarf, they do have different composition than the stars in the main sequence, and also then the supergiant and giant. Because why? Because different of the temperature and also the radius. So the HR diagram here, in fact, show the various stage of stellar evolution, how stars pass from the main sequence, how stars pass from the same main sequence in which they can go to giant sequence, supergiant sequence, and also they can be a white dwarf. So the entire sector and the evolution stage of the stars, by determining its position, we can carry it out from simply by this diagram. So if we're gonna look up in this diagram, we can easily understand that we do have three parts, which is the white dwarf, the main sequence one, which is the sequence that almost show an important branch in the diagram, and the sequence of supergiant and giant. So if we can talk about what is the host luminous stars, is the stars in the top left, which is the stars here. They are considering by a very higher temperature and also a very higher luminosity. They are so bright and so hot. And then if we're gonna consider what is the less hot and less, let's say, bright stars are the one we're gonna start in the main sequence, which are the stars here in this part in the bottom right that present a low temperature, and also they present a low luminosity. So the diagram here shows for us three main parts that present a group of stars in various in various evolution stage. So by far, we can see that the most prominent feature is the main sequence, because it takes the most of the HR diagram. So stars usually spend their life, or spend 90% of their life in the main sequence, because they burn, they grow, and they evaluate. So this is why stars, they spend 90% of their life in the main sequence. So then we're gonna start one by one. The main sequence starts in this part, which is the dominant part in the HR diagram. They are usually characterized by low surface temperature. Usually they don't have a very high temperature. They're characterized by a higher luminosity. Why? Because they do have large radius. They're also characterized by luminosity. If we consider the Morgan luminosity class, they do have luminosity at the level of 5, the class 5. And the stars enter this stage when they have exhausted the hydrogen fuel and started to burn helium and other heavy elements. When the stars go to the main sequence, that means they do have enough temperature, enough size, enough radius to start the nuclear fission and start the first step or the first path in the main sequence by starting the nuclear fission to burn hydrogen and to helium. So stars go to this part when they put the first stamp, which is burn hydrogen and to helium. Then the second part is the giant and the supergiant stars. They are usually, the giant and supergiant stars, they are usually here. They represent a higher temperature, and also they present luminosity between 1 through 3. And they're characterized by a low temperature but higher luminosity. And then then we're gonna talk about the white dwarf stars, which this part of the diagram in which they are characterized by a low to intermediate mass stars. They do not really have higher mass. And then they are very hot, because the temperature here, it shows like white dwarf are usually very hot stars. And then they are characterized by a low luminosity due to their small size, because they present small size, so usually the luminosity is really very low. So according to Morgan luminosity class, we do have the class D, which is destined for the white dwarf stars. So here's the HR diagram, and here's the 3 part. So for the HR diagram, what we can understand from it, the sun, in fact, we can understand from this diagram that the sun is formed in the main sequence with a luminosity of 1, and the temperature is around 5,400. Here is our sun. If we're gonna check, the luminosity is something around 1, and for the temperature is 5,400 degree Kelvin. So here is our sun. So from the HR diagram, studying the evolution of stars, we can understand in which level our sun is, like to check the temperature of our sun, to check the luminosity of our sun, understand its composition, and its future steps. So this diagram, in fact, let us understand what? Understand that the temperature and the luminosity of stars is something determinable from this diagram. Understand also how we determine the size and the age of the stars through temperature and luminosity measurements. Because through the temperature and luminosity, we can understand the size, the dimension, the radius, and also the age of the stars. Summarize the evolution of the stars from the main sequence to the white dwarf to giant, supergiant, to check how stars evaluate. And also estimate the age of the cluster from where stars appear to turn off the main sequence. Go supergiant, giant, or white dwarf. What we can explore? We can explore how the surface temperature affects the observation spectral band, and also how using stellar spectra to indicate stars' temperature, and also how we categorize the stars. This is supergiant, this is giant, this is white dwarf, this is in the main sequence. And why we are doing that? The answer, in fact, is so easy, because to understand the evolution of stars, let us understand how our sun born, how it's evaluate, how stars live and die, and consequently to understand how the solar system generate, how the planets come like that, and how gonna be our future, or the future of our planet Earth. So for this point, I would like to back again to this slide, because it's really summarize all. So some of you usually ask the question, how the stars will end, how the sun that we have it in the morning and when we have on the sunrise, how this beautiful stellar object gonna end. In fact, we are here in this stage, which we do have a protostar that afterward become the sun, which is the one that we see it every day. After that, here we are in this stage right now. Then our sun gonna be a red giant, because it's gonna increase the size and it's gonna turn to burn the helium and the carbon, and then the external layer of the sun gonna extend in the universe to barren planetary nebula. In this case, we're gonna have white dwarf, or we're gonna have type 1 of supernova, which is a binary system. The supernova type A1 is a binary system that connects a white dwarf with another white dwarf with a small size. The both of them emerge together to form and to generate the supernova type A1. So, if we consider that the sun is formed, what's next? What we're gonna have next? When the sun is formed, and if we consider that the sun is already born and start its activity, particles continue to accumulate. They will not stop. They will attract each other to form planetary embryos, and from the planetary embryos, we're gonna have the planets. So, usually, if we consider that, as I say, the sun starts its activity and start the solar activity and inject the temperature. So if we consider this point, the regions which are closer to the sun, usually they are so hot, because the temperature is really higher due to the solar activity, which affects the distribution of elements in the solar system. Because, for example, for gasific element with a very higher temperature, they're gonna evaporate. They're not gonna disappear. So usually silicate and metal are which they're gonna form the rocky planet still closer to the sun, because they could really survive higher temperature that could attain 500 degrees Kelvin, while the molecular water, ammonia, carbon dioxide, methane, nitrogen, and other gasific elements, they cannot survive in very hot temperatures, so they're gonna disappear or they're gonna go far away from the sun. So if we're gonna back, when the protostar form, the protoplanetary disk and particles there continue agglomerating to form embryos of planets that afterward gonna generate the planets, comet, asteroid, and gonna generate many things. So here is the procedure of evolution from the protoplanetary star until we have a solar system. But in fact, it's not that easy, because to have a planet distribution according to this is very controlled with many factors. Here is, for example, the rocky planet, and here is the gas planet. The rocky planets are usually formed by metal, silicate, with elements that could survive really higher temperature, while the gasific planets formed by hydrogen, helium, methane, and ammonia, and different gasific elements, in which we found them far away from the sun. The formation of the planet, if we're gonna see them here, it's not that easy. It's like, okay, we have the sun, and then we have the planet. In fact, it's not that easy at all, because it's absolutely controlled with very important parameter. I'm not gonna cite all of them, but I'm gonna cite the most important parameter, which is, here we're gonna talk about the Roche limit. So what is the Roche limit? The Roche limit, as like the gene instability, as like the mass and the radius of the gene, is an important limit in which we should stay outside to form a planet, to form a satellite, to form a moon. So this radius we call Roche limit, which is a certain specific limit where the tidal force is less than the gravitational force. So here is the Roche limit. In this part, in the left, the tidal force is much more important than the gravitational force. And what's gonna happen is that the tidal force will be very important. The tidal force will be very important, and compared to the gravitational force, any object go inside the limit of Roche will be exploded in small pieces, forming a ring of a particle. And that's the explanation for a planetary ring, like Saturn or like Uranus or Neptune, all the planets that have ring, because the celestial body that just were around here go inside the rock limit, so it was exploded, it was destroyed in a particle, and they form a ring around the planet, like the rings of Saturn. If the object stay outside of the Roche limit, it's gonna survive, because the tidal force is gonna be less than the gravitational force, so it will not affect the celestial object. So the Roche limit is proportional to the density of the planet, the density of the satellite, and also to the radius of the planet. Then another important parameter is the libration velocity, which is the speed from which a celestial body has escaped the gravitational attraction of another star. But if we're gonna consider the solar system, any object, any planet, any satellite realized from gravitational attraction from other objects, it will always remain under the attraction of the sun, because the biggest object in our solar system is the sun. And absolutely the basic or the fundamental law everywhere is Newton's law of universal gravitation. Two objects with two different masses attract each other with the force proportional to their mass, inversely proportional to the distance that separates their center. The last one is Kepler's law. This law, in fact, is very important, because it does not explain only the formation and the evolution of planets in the solar system and their rotation. No, because it also explains many other things. The first law, which is this one, was generated in 1609, The first law says that the orbit of every planet is ellipse, which the sun located at one of the focus of the two focus. The orbit of the planet should be ellipse, and the sun should be in the left one or in the light focus. This is the first law. The second law, it was also generated at the same year, which is say a line joining a planet. This is a line joining, if we consider here is the planet, the line joining the planet and the sun sweeps out equal area during equal interval of time. If we're gonna consider that the planet is here, this surface should be equal to this surface. Even if they don't have the same shape, they should be equal. The surface should be equal. This is the second law of Newton, and then the third law was generated in 1618. It says the square of orbital period of a planet is directly proportional to the cube of the half major axis of its orbit, which we expressed here A. A is the half of major axis of the orbit. It's proportional to the half axis and inversely proportional to the mass of the center and also the constant of universal gravitation. So then I'm gonna stop here, otherwise I'm gonna go inside another topic and I'm gonna talk about what makes the planet at the same equatorial part of like the solar system and the stars. So this, in fact, research, it was part of my thesis degree, of my master thesis degree, because I was working about the origin of the solar system and also about Mars. So here's some reference that I use it for this research, and I would like to suggest it if someone is interested. And also I would like to suggest some interesting books about stellar evolution, galaxy evolution, the origin of the solar system, and all the different laws for Newton's universal gravitational law, and also Kepler's law, and all the conditions that I was talking about. And then I would like also to attract your attention for the NASA ebook, in which they do have several books about Hubble Space Telescope, talking about galaxies, masses, and also some great image, in which you can download them all for free. And I put it here, the website, in which you can just go there and click on and download any ebook that you want. And at the end, if you are interested, I would like to give you some cool contact of association or astronomical group working in this topic, and you can absolutely contact them in case you are interested and you wanna just join their committee. And in the end, I would like to thank you for your attention and for your time, and I will warmly welcome any question.
এখন প্রশ্ন উত্তর সেশন করব, যার যার যে কোনো প্রশ্ন তোমরা কমেন্টে জানিয়ে দাও, আমরা ম্যামকে ট্রান্সফার করে দিব। Do you guys have any questions? Please let us know. Do comment below. Okay, someone has a question. How do particles disperse into rings around planets? The very first question.
In fact, it's a good question. As I say, particles form a ring around the planet when they go inside the Roche limit. The Roche limit is the minimum limit in which we cannot depass it. Because if we're gonna depass it, the tidal force is gonna be much more important than the gravitational one. So the particle cannot in fact agglomerate. So what's gonna happen, this particle will be exploded and broken into particles, and it's gonna turn around the planet, because inside the Roche limit, the tidal force is much more higher than the gravitational force. So the tidal force will not let particles agglomerate together to form a satellite or to form a planet. And this is why the Roche limit is the minimum in which we can class or put there a satellite or a planet outside of the manifestation of the tidal force, because inside the Roche limit, the tidal force will be much more important than the gravitational one, and that's consequently will not let particles accumulate together, and which absolutely generate the rings. For example, if we're gonna see the rings between Saturn, we are not it's not confirmed yet, but the rings between Saturn could be satellites in which was turning around, or it was closer to Saturn, but when it got inside the Roche limit, it was exploded in particles, and they cannot agglomerate because the tidal force is much more important. So what they're gonna do, they are just like that, exploded particles and turn around Saturn in following some specific orbit.
Okay. The next question from Anirban Dash. What's super gas comet? Have any super gas comet in our galaxy?
What is what?
What's super gas comet? Have any super gas comet in our galaxy?
In fact, with super gas, I didn't get the point.
Okay. The next one is.
No, I didn't get the point. What do you want to mean by super gas?
Okay.
In fact, in our galaxy, we do have gas because, as I say, the life cycle, if we're going to talk about human life, the human life or the human time scale is very short. It's nothing compared to the stellar evolution. In our galaxy, the Milky Way, absolutely, we have a lot of clouds of gas, of primary material and molecular material. All this gas in our galaxy, they are distributed in different regions because stars born, life, and end. And when they end, they can give the generation or the life for other stars and for other planets. In our galaxy, we have several billion of stars, several billion of clouds, of molecular clouds that will and want that at the present, at the current and nowadays, they are generating new stars, and also in the future they will keep generating stars. So if we're going to talk about the Milky Way galaxy, absolutely. In our galaxy, we do have several billion of molecular clouds that are ready and preparing to generate stars.
Okay. The next one is, in which case, white dwarf is turned into giant gas planets? From Khan Shomik.
Yeah, in fact, white dwarf, they do not turn into the white dwarf. I'm gonna show it in the slides here, which is the best slides that I like. Okay. Yeah, I'm gonna explain it here. So the white dwarf, in fact, is what? If we're gonna consider the HR diagram, the white dwarf, in fact, they are the previous brown or red dwarf, because the cycle how it's work. It's work then. If the planet, it doesn't have enough mass, it doesn't have enough temperature, it doesn't have enough radius to be a protostar, so because her mass or her size is closer to planetary parameter, to planetary size, planetary mass, so it's gonna be first a brown dwarf. Then it's gonna grow up to red dwarf, and then it's gonna grow up to blue dwarf, and then it's gonna end her life like white dwarf. So if we're gonna talk about the white dwarf, in fact, they are not stars. They are only protostars, try to be stars, but their mass, their temperature, their radius doesn't let them be because they are so small and they do not present a higher or important mass. So if we're gonna talk about white dwarf to turn into giant gas planet, it cannot be, because the giant gas planet, the giant gas star, not planet. The white dwarf cannot be a giant gas star because the white dwarf is not even itself star, so it cannot be. But the white dwarf to turn into a giant gas planet, it's possible because this mass, this radius, and this temperature let her turn herself to a giant gas planet. How, the question, how we pass from that step to that step, from burn white dwarf to giant gas planet, is by the nuclear fission. Because the nuclear fission is an important parameter to start the fission of hydrogen into helium, because it's going to increase the temperature, it's going to increase the size of this object, and also it's going to increase the composition of this object, because to turn from hydrogen to helium and then from simple to heavy chemical element is basically controlled by temperature.
Okay. The next question is from Pushkar Dahal. Why the black hole emit the radiation but even light can't pass through it? Very interesting question.
Because yeah, I'm not very expert in the black hole, but I'm going to explain it, because the black hole is still mysterious things, because all astronomers around the world and the current research, the current study is not really let us to understand perfectly the mechanism of formation of the black hole and their evolution and their function. The black hole represents a very high gravitation. It's unbelievable. Even the light there, when it passes into the black hole, the light itself cannot escape, because the gravitation itself is so important. So the black hole, I would like to say, is something very mysterious. We cannot understand, and until nowadays, it's still really something mysterious, obscure. We cannot really understand from how it's come and how it's like that. We class it like a black hole, but yes, we need more research in that topic. What I would like to say about the black hole, the gravitation there is very higher. Even the light cannot escape. Nothing can escape from there. But yeah, don't forget the gravitational. I'm going back here and again to the slide. The gravitational, the black hole, in fact, is the result of the explosion of supernova type 2, which is the type 2 supernova is the explosion of two massive collision, or the combination between two massive bodies, or it's the result of a blue supergiant, which also in this case is a very massive and big object. So the black hole, it should be light, yeah, we can detect it, yeah, but in the spectra and also in the infrared, not in the visible light. But yeah, still really something mysterious. We cannot really understand it perfectly.
Okay. We got another interesting question from Hafsa Fariha. Does the angular velocity of a star increases if the radius of a forming star is reducing? Does it spin faster? Nice question.
Yeah, as I say, the radius of the star, and as I say, the radius of the stars and the angular momentum and the solar velocity is three important parameters. Because if the radius is important, the velocity is gonna be slow. If the radius is small, the velocity gonna be higher. It's the same example of the scaling spin that I showed to you. So the angular momentum, in fact, is constant. Whatever the object is, and whatever the velocity or the radius, the angular momentum is always constant. And I'm gonna show you why. So here is the angular momentum. The angular momentum is always constant. Since we do not have a twisting force, since we do not have a force from outside the celestial object, the angular momentum is always constant. Why? Because the angular momentum depends on the velocity and the radius. If the radius are increasing, the velocity is decreasing. So we're gonna have angular momentum. Then, if the radius is decreasing, the velocity is increasing. So the angular momentum, we have it here. So they are playing like that. It's the same for the molecular clause. They are just playing game. If the other one increase, the other one gonna decrease. If the other one increase, the other one is decrease. So this procedure, increase, decrease, increase, decrease, gonna make the angular momentum constant. It's look like you are riding a bike. For example, you're gonna ride 3 kilometers in 5 minutes. You can do it slowly, but you can do it faster because you are able to control the distance and the velocity. So the angular momentum is like that. The radius increase, the velocity decrease. If the velocity increase, the radius is increased, which make the angular momentum constant. So whatever the radius or whatever the velocity of the stars, whatever they are, in the beginning, during her life, and in the end, they're not gonna change the angular momentum because the angular momentum is constant.
Okay, one more question from Tanny
Mhm.
Roy. What's the main reason of being singularity inside a black hole?
I'm not a black hole expert, but yeah, as I said, black hole is really still something mysterious. So yeah, the singularity also there for the Big Bang theory because the singularity also it was studied by Newton, and yeah, something honestly is still math. No one is really understand it perfectly. But yes, something also some have also some issue and also some problem in the Big Bang theory because it's still really the most accepted theory, but it's not really homogeneous or parallel to all the law in physics and also in math, in astronomy. So talking about the singularity, I'm gonna say I'm not really expert because it's also part of the Big Bang theory, which is classified really as a cosmology field. But yeah, it's something really I cannot answer because it's still not really clear about the black hole and also about um, the black hole, also their evolution or their what is their characteristic and their parameter. For example, why the black hole present the most higher gravitation in the world? We don't know why the black hole absorb even the light. Why there nothing can escape from black hole? What is inside there? Still, like really a question without uh, a clear, perfect answer because we need more science, we need more research to answer this question.
Okay, one more question from Ryan E. Rabbani. What's the source of energy or fuel of white dwarf stars?
Yeah, the white dwarf star, in fact, as I say, they are not a protostar, but with a very, very small size. They do present small size, in which their size, their temperature, their radius will not let them go to the next step, which is to be star. So the white dwarf stars are protostars in which they do have hydrogen, and this particle turn or agglomerate, like condensate in the bottom of the stars, which generate the increase of the temperature and also the increase of the density, which make the star more hot. And when we're gonna talk about gravitational collapse or gravitational contraction, because the protostar it was like that, Here we have the protostar, and around it we have the rest of the particle. So the white dwarf, they are stars, but they agglomerate, they condensate, and the particle go inside to the bottom. So this gravitational contraction generate an energy. And when we're gonna talk about energy, that's mean temperature. So the gravitational contraction of the white dwarf is the main source of the energy and the temperature of this protostars. But they do not really have enough temperature, or they didn't achieve the normal, let's say, limit to be a star. But they present important. For example, if we're gonna back here to the HR diagram, we can see that the white dwarf, yeah, the white dwarf, they are present in each air diagram, but they present really, yeah, they present really a less up. Where is my slide? Yeah, they present really a temperature that could be less or higher, depends. Because, for example, here is the blue dwarf, because the cycle is white dwarf here. because they start like a brown dwarf, red dwarf, blue dwarf, and white dwarf. They start like that. So the white dwarf is the last level here, which they present a very low temperature. And also their mass is very low because their radius also is very low. So they still present some mass, and also the gravitational collapse, as I say, is the main or the principal parameter that generate the energy. And when we talk about energy, we're gonna talk about temperature.
Okay, ma'am, this is the very last question we will take from Guismi. What's the difference between astronomy and astrology?
Ah, that's a very important question. What is the difference between astronomy and astrology? Astronomy is science. Astrology is not a science. Yeah, in fact, astronomy is based in research, based in calculation, based in statistics, based in mathematics, based in physics, astronomy, geology, biology. Astronomy and astronautic studies are a science. It's something real. You can calculate, you can determine it, you can analyze it, you can make your statistic, you can study it, you can prove it, you can explore it, you can investigate it. Astrology for me is a field, I would like to say, but it's really so far from science because it's like, for example, for me, I'm against astrology because I really do not consider it like something linked to science, but it's still like a field which is far away from science, because astrology is to believe what is in the future and use a constellation and also use some celestial bodies movement or ephemeral calculation to say, okay, in the future you're gonna have a lot of money, or you're gonna have a car, or you're gonna be rich, which is not, because it's not something really we can prove by science. So it's two different fields. For us astronomer, we're gonna separate the both. We want to separate astronomy from astrology because it's not the same at all. Astronomy is science, it's calculation, it's measurement. Astrology is not. So it's not the same one. We should be careful.
Okay, I guess there is no question. Guys, if you have any question, if it's not, then we will end of this session. Okay, thank you so much, ma'am, for your precious time. We know you are quite busy, but you gave us your time.
Now, I would like to thank Rifat, and I would like to thank all the working group in Bangladesh Astronomy Research Center for the organization of the event and also for the idea of the meeting. I would like also to thank you all for your effort and for your participation, wherever you are here with us on the platform or following us in the social media. Thank you, everyone, and thanks again, Rifat, and thanks all the group for that nice meeting today. And yeah, I hope to see you soon.
Yeah, we will see. Glad to see you, ma'am. ওকে, যারা যারা লাইভ টকটিতে অংশগ্রহণ করেছো তাদেরকে অসংখ্য ধন্যবাদ। অ্যাস্ট্রোনমির দারুণ সব ব্লগস এবং নোটস পড়তে চলে যাও আমাদের ওয়েবসাইট www.barkbd.org. Okay, ma'am. Thank you so much again, and see you soon, ma'am. Take care.
Thank you. Bye bye. Bye bye. Thank you.